Right. So you might be wondering why I didn't post anything today. Um, yeah, I mean, my day was really not good. Uh, right. I mean, I was just doing this conic parameterization stuff, which, yeah, honestly, is just so complicated. I don't know why I even started this thing. I mean, I thought this would be a nice um, thing to do because it will give me access to something more intuitive rather than just separating each conic into its individual case. Right, it did give me something more intuitive, and that is the fact that um planetary orbits can be easily done using this parameterization because it's only centered at the focus. But other than that, in actual maths, it's not useful at all. I mean, really, just going from one view to another, just shifting the graph, even something as simple as that is just so horrible when you use this parameterization. So I would recommend, um, if you are watching this, just watch if you are curious as to how this parameterization actually looks um, on the 2D plane, right? Other than that, it's not even useful. Watch that other video I made. So there you will see how this was derived, and yeah, every other detail about this, and also how to apply this to um, yeah, like inverse square law. Whenever your force goes by the inverse square law, how to apply this in those cases, right? You can see that. I mean, honestly, it's just more or less a simple proof of um, why the orbits of planets are actually elliptical or hyperbolic or whatever, right? It's just a simple proof of that. That's all that last section will be for that video. um, right. I really don't know what to say. Anyway, so now to the topic. What is this, first of all? Right, so this parameterization that I got in that video, I just graphed it out. So first of all, this black curve is just that curve, right? A cosine t upon 1 minus e sine t. So I did not have theta as something that I can use to plot. So I just used this thing, right? No big deal. Okay, so, right. How does this change as we start to change the eccentricity? Well, first of all, why don't I have a slider for eccentricity? Because, yeah, just to maintain more control on how the eccentricity changes, I made this function in M for our E, so that when I change M, E will change according to my wishes. That is, it will stagnate. So, okay, let's just show you the thing. So oops, as M will change, right, it's gonna stagnate at one, so it almost pauses over there for one moment. It just stops. That's what I wanted to do. That's why I'm using this function. And you might be seeing a lot of points over here, some of them not even meaningful. Like, what's this M? Okay, P is just a point on this curve. Okay, what about this S double dash? You don't have a third focus. What are you talking about? I will explain everything in detail. I mean, D1, D2 are not that bad. You can easily understand what D1, D2 are. Oh, so I don't have D2 right now because I only have one directrix graph. Right. Okay, let's just first of all see what's going on. So first of all, you have these two black curves. First, you have x equal to minus d, which I labeled as d1. So this is the directrix, and then the focus is our origin, right? And this black curve is our conic. M is just a dummy variable that I vary to change the eccentricity. So whenever M is 0, eccentricity is 0. Whenever M is 1, eccentricity is 1. Okay, come on, go. Oh, yeah. So now it's a parabola, as you can see, right? Eccentricity is 1. So look at that. Whenever it's more than that, eccentricity is more than that. Right. Cool. What about this n thing? This n is just a scaling factor. So if I change this, yeah, this happens. So it just shrinks this. Now, when it's parabolic or something, you won't understand what is in fact going on. But let me just make this elliptical so that you can get a better better picture. So yeah, it just shrinks and inverts and whatever, right? Okay, what's this U? So this U has to do with the position of this point P. Let's not get into that first, right? And then M and S dash are dependent on P, but whatever. The thing is, wait, right. The thing is, these two black curves need to first of all understand what's going on with these. Okay, what's happening with my mouse? Yeah, so let me just show you how this thing changes as your eccentricity changes. So first you get, some kind of hyperbola when eccentricity is bigger than 1, then this goes to parabola, then ellipse, circle, then it goes back, and you get the idea. Okay, changing n doesn't really change everything all that much because it doesn't alter the shape, right? So there we go. Let's go to an ellipse. Okay, right, and then a is the thing. So you should really watch the other video that I posted today. You will have a better understanding of what a actually is in that case, right? So a is something like the distance between d1 and s, but that times the eccentricity, right? So d is just a upon e, you can say, right? So that's the way I defined it. I have defined d as a upon e, and small a is of course the semi-major axis, which is a upon minus e squared, right? So a times 1 upon e minus e, that would be capital A. Sorry, that would be capital D. But capital A would be eccentricity times that. So it's going to be a times 1 minus e squared, and that's why small a is just capital A upon minus e squared. Anyway, and then I have this r. R is of course just the distance from S to P, and then I have x and y, which are the coordinates of P, right? Then I have v, which is equal to u minus arctan of d upon y. This thing is the angle made by the tangent at P with the x-axis, right? So this is giving another important thing, which is that the angle between the tangent and the vector joining S to P, right? That angle is given by arctan of d upon y, right? Okay, and then what's this t? Okay, you don't have to worry about that till now. Then some points I'll explain. So first of all, 0, 0 is our focus, first focus. Then you have the other focus, which is at S dash, which is 2 small a e, comma 0. You have the center C, a e, comma 0. You have this directrix, so the feet of perpendicular, I mean the point where it cuts the x-axis, right? That thing is labeled as D1. And similarly, you have a T2. I'm not showing that directrix. I should really show that. So this is the other directrix. So this is the other directrix. You can see what T2 is now. Right. Do we have to actually, okay, whatever, just leave it like that. And then what is this thing? What's happening with my mic now? Oh, come on. Just wait a second. I think this is not, oh yeah, now it's working. Okay, and what is this thing? This thing is of course the auxiliary circle. So for ellipse, it's pretty clear what the auxiliary circle is. Let's just show you what auxiliary circle means for a hyperbola. So notice how it changes. First of all, it's a finite auxiliary circle. It's if you zoom out really hard, you can see what this circle is. I mean, you can see the whole circle, right? You can see the curvature. But then when it starts to approach 1, so whenever m starts to approach 1, that means e is also approaching 1. This circle basically goes to infinity. That is, this guy's center goes to infinity, but this point, so where it's, so the other diametrical point also goes to infinity, but this diametrical point stays here, so it's finite. Although it is changing, it's still finite. That's important, right? So that just means that a parabola is basically an ellipse with a really big auxiliary circle, or you could say the other focus going to infinity. That will do it. Okay, and then something crazy happens after that. So if you increase a bit, you can see how the curvature is changing, right? So first it was concave towards right, and now it's concave towards left. Any guesses what might be happening? Well, I guess that the center of this circle is now completely to the left. So first it was like at positive infinity, now it's at negative infinity or something. I mean, of course, doesn't actually look like it's at negative infinity because then it would just be straight line. It is, I mean, a very large value, but it's negative, right? And then as you increase that, okay, now it's clear what's happening. So this is the auxiliary circle. I mean, yeah, it's still between the vertices, right? Those are still the diametrical ends, right? But now it's contained outside of the hyperbola, or you could say in the hourglass region. I don't know, right? What do you call this region? I don't know. This is the inside of the hyperbola, right? So this must be the outside, and it's contained over here. Okay. Oh, come on. Why is my mouse not working today? Right. Okay, so just go back to ellipse now because ellipses are ellipses are like much easier to deal with. Because I mean, okay, some of my graphs that I have, those will only work on ellipses completely. They will also work on hyperbola, but at some parts they don't work, right? So that's why ellipses are better to use. Okay, now let's get to it. Oh, first of all, by the way, how do you get this thing? I mean, it's not that hard. Just write this guy's coordinates. I don't know, using complex numbers or anything. That's the easiest as I see it. And then differentiate with respect to time, right? So just put that times so dt upon dt at the front, and then whatever vector you will get, right, for the velocity, just take the unit vector along that, and then you just have the direction of the tangent, and then after that it's easy to figure out the slope is and everything. So right, that's doable. There are some graphs that are not that easy to do. Yeah, and that's why this is not a great way to do conics, because it's good and all when you, I mean, have computers helping you, but then in a test you won't be able to do all these calculations, right? So I mean, yeah, how do you figure out the uh, angle separated on the other, what do we call it, the other focus, right? You can't in this format. But instead, if you had everything centered around c, I mean, it will still be really hard, but then you have a less complicated parameterization, so it's still okay-ish, right? Okay. And now what's this t thing, right? So before knowing what t is actually, okay, maybe I should tell you what. Now, first of all, I will show you some other graphs because it's involved in here, right? So this orange graph is for this directrix. Just zoom out. This thing, t cosine u comma t sine u, it's just a parameterized line segment, so this line segment. And then this thing is the tangent. So x comma y is just this point, and then a parameterized vector added to this point that gives us the parameters of, sorry, the coordinates of any point lying on this line, and that's this thing. I mean, it's from negative 100 to 100. You can put anything you want. Okay. And then you have this thing. Wait, what was this thing? I just forgot myself. Oh, right. So it's this line segment. So s dash p, right? So yeah, I mean, 2a e comma 0 is this point, and then you got this vector going from there to there, and then the parameter t as it goes from 0 to 1. Cool. Then you have this. Oh, right. So it's the extension of this line to that. Right. I mean, okay, that is. Should I show you what this thing? I think, yeah, it can't hurt possibly. Okay. So this thing is an extension of this. And first of all, I should show you this. So what's this circle? This circle is also centered around this focus S. And the thing is that this circle has radius 2a, so 2 small a, as you can see. Okay, and let's just join all the lines now, because then you will understand what's going on. Right, so first of all, what's m? M is just the point. Wait, sorry, what was it? Oh yeah, okay, so just extend this sp till it meets the auxiliary circle. Yes. And then you got this tangent over here. So whenever you reflect s dash about this tangent, that image will actually go to this point. So yes, these two will in fact be exactly the same point. That's kind of important, you know. How do we know for sure? I mean, you can do some easy geometry. First of all, these two angles must be the same. So angle s dash pm and then s double dash pm, this is the same, you know, reflective property, right? Because sp, whatever this angle is, right, that's the same thing as its vertically opposite angles, right? And then the thing is, sorry, what was I saying? Right, these angles are the same. You got this side which is the same, and then you got these right angles, right? So yeah, this is actually important. um, so the feet of perpendicular from any focus onto the tangent, that feet of perpendicular actually lies on the auxiliary circle for an ellipse. So using all of these properties combined, you can finally see that yes, in fact, this configuration will be what you will get. And from this, it's pretty easy to see that okay, this sum, so SP S dash, this length is in fact the same thing as SP S double dash, but then that length it's just, you know, 2a, and that's why the, you know, sum of lengths is equal to 2a property, that thing works. Yeah, until that point we wouldn't actually be using this property in any way. We will just be using coordinate geometry, and of course there's the easier way of just, you know, finding out these lengths and then boom, you got a thing. Right. Yeah. Okay, and yeah, like reflective property you can easily see because these two angles are the same. We can also try to prove this. I'll leave that to you, really. Okay. Right, and then now let's go to, where did that go? Okay, where did that go? Capital T. Okay, this curve. Sorry. Right. Okay. So, what was capital T first of all? Capital T is just the length PM. So, okay, where did that T go? Right, this length is just the length PM, which can be, you know, done using a bit of coordinate geometry. It isn't that hard, I think. Right, I mean, you already know what V is, and now that you know what V is, you can actually figure out, sorry, not V, you just want this angle, so that angle is just arc tan of D upon U. And once you know that, and of course you also know what this length is and everything, so in the end you can just figure out what this should be. No big deal, easy, right? Okay, and yeah, okay, this s double dash s dash, I got that when I made the normal vector of this tangent, right? I added that vector to the point M, and M was just given by x plus capital T cosine V and y plus capital T sine. I should have also, I think, written it somewhere over there. Do we have it? Yes. So this point, right? This is capital M, and then just add to that this other vector. I mean, a scale multiple of that, and let T go from the maximum that this could be, so maximum length, which is 2. What's this thing? TD upon y, because of course like tan of this angle, so that's T upon y, T times of that. That's going to be this thing, and then negative, right? So you do this thing, and you'll get this line. Okay, so this is nice and all. That just, you know, once again do that eccentricity stuff, so that you can see this in its full glory. Oh, and by the way, also I should change you so that you can see what is happening. So the reflective property holds everywhere, you know. And yes, I restricted this to just pi because tan inverse is only defined on a certain domain range, and that's kind of problematic for me. I wish there was some kind of function that would just, you know, take a vector in it and then give us the angle subtended, the angle made by the vector with positive x-axis. If there was a function like that, I would be so happy to use that everywhere. I really do wish there was a function like that. Whatever. Okay, so now that that's done, let's just do this thing. So you set that to something small, and n. Oh, and by the way, okay, I think I should say that. Right? Okay, no, let's not. Let's not do that. We'll do that later. Okay. And then let's just, right. Now you can see what's happening. Weird, isn't it? Yeah, it's just like so full of stuff that. Oh, okay. In fact, wait a second. I only showed you what's the case for the ellipse. So let me also show you what happens for a hyperbola. So right, a parabola now. Oh, and by the way, for the parabola, you see this line. That's the line joining P to S dash, and this just completely becomes horizontal. And then using the reflective property, you can say that these two angles are the same. But yeah, that's like saying that any ray just coming from here to here horizontally will in fact reflect and go to S, right? Yes, so basically a parabola is just an ellipse with S dash at infinity. And that's why this thing works, right? Uh, cool. And okay, this thing doesn't matter. Yeah, then got its tangent and whatever, right? I also wish to actually, graph out the asymptotes, but then I thought, okay, no, let's not do that because that would just be too much of it going inside, right? I mean, it's already hard to actually see everything clearly when it's all moving, so that would be even harder to see and also unnecessary. Why would I want to do that? Because in the end, this doesn't even matter. This parameterization is like really, really, useless. Why would somebody use this? Okay, right. So for the hyperbola, so just a tiny bit more. Okay, actually more, quite a bit more. Right. So okay, first of all, is cancel out some of these graphs because they are hindering the vision. Okay, cancel out this thing. Estimate dash around one. Okay, so now it's completely just the tangents and these two lines. So you can still have the reflective property. So this angle is the same thing as that angle, right? Uh, yeah, right. And as you can see, S dash and S are now inside the hyperbola. Before that as well, they were actually inside the conic, um, right? But now it looks like that these are outside of some certain, no, it's actually inside of the hyperbola, and these are still outside, but now these are near. Isn't it weird? It is as if your ellipse got stretched, really stretched, and then you're actually stretching it around some kind of cylinder and it came back, right? Except that it doesn't actually behave like that. It just behaves like two lines. So if I zoom out, I just keep on zooming out. You will see that it's like just two lines basically when you zoom out really hard. And that doesn't look anything like an ellipse. Yeah. So really, hyperbola is a different curve. It's not an ellipse. Parabola, okay, you can say maybe it's an ellipse because it shows most of the properties that an ellipse does. Uh, but hyperbola, no, 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 right? It's so much different. Okay, uh, right now time to. Okay, why is my mouse not working? Come on, don't do this. Right now it's working. So yeah, this is not required anymore. Now let's just put back some stuff. So once again, S double dash is the reflection of S dash about this tangent, right? This circle is just a circle that has S double dash on it, and then it's centered at S. So yeah, right. Uh, oh, and by the way, this is auxiliary circle. This auxiliary circle, wait, okay, this has M. Yeah, even now it actually has M, because it's the perpendicular from S dash to right. Actually, I should make that line happen as well, right? So you can see S dash to M, and then this is perpendicular to this tangent, and then forward with the same length, you go to S double dash. So it's still working out, except it's not really giving us anything nice. Yeah, and okay, maybe just maybe this might uh, show us something. So for an ellipse, what was the thing? It was that you know um, sp plus s dash p would be some kind of constant. For this guy, sp is this thing and s dash p is this thing. So I mean, of course, the difference of that is a constant, but how do we get that? Right, so these two lengths, uh, Okay, no, 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 no. Wait, what was I doing? So I just want this length minus that length, right? Yeah. Uh, right. And then this length. Okay, okay. It's not actually that easy to see what's going on, right? So for an ellipse, what was the thing? The thing was that this length from S to S dash, right? That in fact was the sum. So where's S? Okay, S to S dash. This thing was the sum of the lengths. Now we would expect this to be the difference of the lengths as well, right? Is that obvious? I don't think so. We got these as the lengths. Oof. Yeah, it's actually not obvious at all. Yeah, right. Uh, uh-huh. Of course, of course. Right, so that length. Oh yeah, so I just have to make that connection once again. So S dash P, that must in fact be the same thing as um, S dash S double dash, right? So oh, come on, why is this not working? My mouse is just not working. Once again, what was the thing? Um, was it S dash P? No, it was P S double dash. Ah, right. So this length and come on, why is my mouse not working? So this length is the same thing as this length, yes, right? So the difference between this length and that length, that's the same thing as the difference between this length and this length, which is of course this length. So right, and then this length is always constant. It's gonna be 2a, and what does that mean? That the difference between these two is always 2a. So this also works for a hyperbola. And then of course there's the more classic proof of writing these as eccentricity times the distance from the directrices and then doing the thing. So the difference remains a constant, although it doesn't actually tell us right away what's going on. It's not geometric, right? It's more algebraic and whatever. Now it's done. Okay, so let's look at the next video. Bye. Oh, sorry. This is say and okay, bye.